Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to talk about how to arrange substances in order of increasing boiling points. So let's get into this. So the first thing we need to do is read the question. So here we are. So it says arrange the following in order of increasing boiling points. And so they're giving us these five different substances. So we have 0.1 molal of KCl, which is potassium chloride. We have 0.1 molals of potassium dichromate, K2C, Cr2O7, 0.2 molals of sucrose, 0.05 molals of sodium chloride, and 0.1 molal of a weak acid. We're just going to call that HA. That's usually the generic way of formalizing what a weak acid is, or what we're dealing with as a weak acid. So HA. So HA, because of course hydrogen is written first and A means anion. So this is some generic weak acid. It doesn't matter what the identity of it is. The point here is to remember that for weak acids, they will ionize a tiny bit in water. So most of this is going to be in the form of HA. Some of it will ionize in the form of H plus and A minus. Okay, so we need to figure out the arrangement, the order of increasing boiling points. That means we're going to start with the least lowest boiling point, getting to the largest boiling point. So what we need to look at is the change in boiling point when you dissolve something in water. So we got to look at the colligative property of the change in the boiling point when you dissolve something in water. Okay, so we're going to look at all of these things. So in order to get the change in the boiling point temperature due to what you dissolve in it, we have to use this equation here, where the change in the boiling point, so this change in boiling point is a colligative property. It depends on how much particles you have dissolved in water. That's going to be equal to the Van't Hoff factor, which is represented by this small I. This is basically determined by the number of moles of your substance divided by the number of moles of your particles, or the other way around. So the total number of particles that are from your substance divided by the moles of the substance itself. So I'll talk more about that in a moment. And then we have the boiling point elevation constant. So whenever you add something to water, if you dissolve something to water, the boiling point of the solution will increase compared to that of pure water. We saw the same thing with the freezing point depression, right? If you dissolve something in water, then the freezing point of the solution is going to be less than that of pure water. With regard to boiling point, it's going to be the same idea, but in the opposite direction. So when you add something to the water, or whatever the solvent is, it's going to increase the boiling point of the solution. So the solution is going to have a higher boiling point than the pure solvent. So we use this equation. This is temperature dependent, or this will be this constant here is temperature dependent. They don't give us a temperature, but we know that if we're dissolving all of this in water, then this is going to be the same for all of the substances, because this is related to whatever the boiling point constant is for the solvent. And since we're assuming that they're all dissolved in water, then the solvent for all of them is water. So Kb is going to be whatever it is, right? So all we need to do is use this and compare what we get from this with regard to, one, the Van't Hoff factor, and the molality of the substance. So let's start with the first one, so we get an idea of what we're talking about here. So here, what is I? What is the Van't Hoff factor? So the Van 't Hoff factor is basically a ratio of how many particles are formed from each mole of substance that you dissolve in the water. So in this case, if I have 1 mole of KCl, that KCl is going to dissociate into 2 ions. And so I'm going to have a positive potassium ion and a negative chloride ion. So I get 2 particles from one substance. So 1 KCl gives me 2 ions that are going to dissociate. So these are not going to stay together, right? So even though on the bottle it will say KCl, 1 mole of KCl, then in reality, I actually have 2 moles of particles. And the boiling point elevation and the freezing point depression and other colligative properties depend on just the number of particles that are in solution, not the identity of those particles. So whatever number of particles I have, whichever substance gives me more particles, that's going to raise the temperature more. So I'm going to get a change in temperature greater for all more particles I dissolve. So here I have a Van 't Hoff factor of 2. So here I would equal 2. So the change in temperature of the boiling point is going to be equal to I. In this case, I get 2 particles for every 1 mole or 1 formula unit for this. So my I is 2. So I get 2 for my I. My molality is 0.1. So I put in 0.1, and that's going to be multiplied by my KB. It doesn't matter what KB is because everything is going to be related to KB. So when I multiply this together, I get 0.2 KB. Okay, next I can do the exact same thing. So here I have K2Cr2O7. So here I have the dichromate ion, that's 1 particle, and I have 2 potassium ions. So for every 1 formula unit that I dissolve in the water, I'm going to get 3 particles this time. So I get 3 for every 1. So my Van 't Hoff factor is 3. So I here is going to be 3. So for this substance, I get delta T B is equal to 3 times, again, the molality is 0.1, so I'm going to put 0.1 multiplied by KB. KBs are the same for all the substances because we're assuming that the solvent, the solvent is the same, water. And even if the solvent wasn't water, the solvent is the same, so KB is going to be the same for all of them. So it doesn't matter what the solvent is here. But we're going to assume it's water. So here, if I multiply this, I'm going to get 0.3 KB. Sucrose is sugar. That's C6, or actually it's C12. Oops. C12, H22O11. So that's 1 particle. It's a covalent bonded particle. It's a molecule. So this is just one thing. It's not going to break up into different things. So the Van 't Hoff factor is going to be 1 because for every one of these that dissolves in water, I only get 1 particle because this is not going to break apart into other particles. So the Van 't Hoff factor is going to be 1. So here I have the change in the boiling point temperature is going to be equal to 1 multiplied by, here I have 0.2 molal. So it's going to be 0.2. And then that's, oops, I forgot the KB. That's going to be multiplied by KB. And so I get 0.2 Kb for my sucrose. Next, I have sodium chloride. So here I have sodium chloride. For every one of these, I'm going to get 2 ions, sodium ion, chloride ion. So the Van 't Hoff factor is going to be 2. So then this is going to be delta T of boiling. The change in the boiling point is going to be equal to 2 for the Van 't Hoff factor multiplied by 0.05 molal multiplied by Kb, and that's going to be equal to 0.1 Kb. And finally, we have the weak acid. Now, for the weak acid, we know that this is molecular, right? So it's going to ionize in water a little bit. It's a weak acid. If it was a strong acid, then the HA would completely 100% ionize in water. So we would end up with H plus and A minus. So all of your HA would be converted into H plus and A minus ions. And so the Van 't Hoff factor there would be 2 because it completely ionized in water. Now, if this didn't ionize at all in water, like we had with sucrose, then this HA would stay together and none of it would ionize. And so this would be like sucrose where the Van 't Hoff factor is 1, right? So it would, if it ionized 0%, right, then it would act like sucrose and the Van 't Hoff factor would be 1. If it was like NaCl where it completely ionizes in water and all we have are ions, H plus and A minus, then it would be a Van 't Hoff factor of 2. Now, in this case, it's a weak acid, so it's not 0% ionization, and it's definitely not 100% ionization. It's in between. It will ionize a little bit in water. So this, when we write it out, so this is going to be delta TB is equal to, now the Van 't Hoff factor is going to be somewhere between 1 and 2. So if I put in somewhere between 1 and 2, so somewhere in that range, we're going to multiply that by 0.1 molar, or molality, sorry, 0.1. 0.1 molal times Kb. And so if it was 1, then we would get 0.1 molal, or we don't need the molal, times Kb, or if it was 2, it would be 0.2 Kb. So we know that for the weak acid, it's going to be somewhere in this range. We don't know exactly where, but that's not going to be important because all we need to do is order or arrange them in order of increasing boiling points. So the larger the change in the boiling point, that means the higher the boiling point went up when you dissolve this into water or whatever the solvent is. Okay, so now we're in a place where we can order these. So notice we have 0.2 Kb. So all of these are multiplied by Kb. So the only difference is going to be the number in front. So we have 0.2, 0.3, 0.2, 0.1. And then this one is somewhere between 0.1 and 0.2. It's not equal to 0.1. It's not equal to 0.2. It's somewhere in between. So we can go ahead and order this from lowest to highest. So far, the lowest is going to be 0.1 Kb. That's going to be the NaCl. So NaCl is going to have the lowest boiling point. And then we have next we have the weak acid, which is somewhere between 0.1 and 0.2. And then following that, we have the KCl and the sucrose, which are both exactly 0.2 kb. So that means that the weak acid here is going to be the next one because it's somewhere between zero point 0.1 and 0.2 kb, whereas the others are 0.2 kb. So the next one would be your HA, followed by, we notice here that the KCl solution is 0.2 kb, and also the sucrose solution is also 0.2 kb. So those are going to be equal, but they're going to be greater also compared to the HA, the weak acid. So they're going to have a larger boiling point. So that means they're going to be equal. So we'll have sucrose equal to KCl. So these are going to be equal in their boiling point elevation, but both of them are going to be greater than the boiling point of HA. And then finally, we have the potassium dichromate solution that's going to have a delta TB of 0.3 kb. So this is the largest change. So it's going to have the largest elevation in its boiling point compared to pure water. So that means that this is going to be the highest boiling point, and that's going to be K2CR2O7. And that, ladies and gentlemen, is how you arrange these substances based on increasing boiling points if you know the molality of the substance and you know or the Van 't Hoff factor of the substance, and using this equation here. I hope this video will help you out. I hope it did help you out. I hope you enjoyed the video. If you did, then please like the video, share the video, hit that like button somewhere over here, over here. Also, make sure you subscribe to my channel. Help me out here. When you do that, make sure you click on the notification bell up above. When you do that, click on the all button so that way you will be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you if you have a question or a problem you need help with, or you have a topic you would like me to cover. Put that down below. I would be happy to do that for you. Thanks for joining me and have a great day.